Lesson 3-5, zeros of polynomial functions. So if you remember in the past, we said we have these things called zeros. They're also called x-intercepts. And then sometimes if they were imaginary or complex. So it was just when the graph hits the x-axis, the y is equal to 0. So that's why they call them zeros. There are x-intercepts also, and then sometimes we talked about how they may, like if we had a quadratic back at one point and it was up here, that the zeros were actually complex, and so they called them roots instead because they didn't really hit the x-axis. So don't forget we still have that as a situation as well. So if you have this function, x minus 4, and x plus 3, each of those multiplied to get this new polynomial, well, where are my zeros? Well, they're just from studying each of these, because if x were 0, 0 times anything would be 0, that would be 1. If x minus 4 were 0, this would be 0, times these other ones would still make y, your f of x, be 0. And if x plus 3 is 0. So that one's already solved. Add 4 to the other side, x is 4. Add 3, or subtract 3 to the other side, next is negative 3. So at all three of these points, so negative 3, 0, and at 4, the graph is at 0. Now the next thing becomes, well, where is it at all the other places? So in between negative 3 and 0, where is it? Well, you can always test and just see. So if I put in, like, let's say negative 1's in here, right? If I put a negative 1 in here, what's negative 1 times negative 1 minus 4 would be negative 5, times negative 1 plus 3, negative 1 plus 3 would be 2. Well, that's negative times negative positive, so that would be like up at 10. So it's on the positive side in between there. So in between here, it must be doing something like that. Well, what's it doing over on between 0 and the 4? Or what's it doing on the left side of negative 3? So if you put a negative 5 in here, negative 5, that would be negative, and that would be negative 3 multiplied, 3 negatives multiply, so it must be going down there. Well, what's it doing in between here? So let's say we put a positive 1 in. 1, negative 3, 4, that would be negative, so it must be coming down, and then it's going to be going back up on that side. So another thing that they use to describe that, instead of just doing it like I did there, is they use this thing called a sign table. It looks kind of complicated, but it's really the same thing as what we just did. So evaluating at each of the intervals to see if the graph is in the negative or the positive region, and then just make your graph match. So if you like how I did it on that first slide, do that. Just know the sign table, that's really the same thing. It's just setting it up in a chart. Well, so if we were going to sketch it, how did our sketch look? Doesn't it look about the same? Okay, so using their sign chart or the way we did it on the first one, just checking in each of those intervals to see where the graph is. And then what about multiplicities of 0? So what that means is, notice like right down here, multiplicity of the 0 means what's the exponent. So these each have an exponent of 1. So the graph goes through on those points. Well, look at this one. Here's an interesting one. So I have a multiplicity of 2 here. The exponent on x minus 1 is 2. Well, what's the 0 for x minus 1? That's the 1. But what happens because of this 2? Just like on a parabola that has a double root like this, like if I said x minus 1 squared was the parabola, at 1, the parabola shifted 1 to the right, right? So the 1, it just bounces off the x-axis. And then on this one, where when does x plus 2 equal 0? Negative 2, but it has a multiplicity of 1, so it goes through. So what about this one? We have a cubed. Well, a cubed has this effect on the graph. One side of it is a parabola opening one way, and the other side is a parabola opening the other way. That's how I describe it anyway. In fact, when I draw it, if I know I have a cubic or a third degree, I'll put my point there, and I'll draw a parabola going one way on one side and a parabola going the other way on the other side, just to help. Then you could go up with other even or odd degrees, but here's a 4, a degree 4, and look what it does. It looks a lot like the parabola, degree 2. It's just that it's a lot flatter right in there, and then afterwards it's actually steeper. So, and then you could do degree 3, 4, or 3, 5, 7, etc., and see that they were similar to the 3. So that's just a kind of an example of knowing what the different shapes do. But then here we have one more. This one has to have more degrees. It's not just a parabola, so it's higher degree than 2, but there's only one 0. There's a 0 at 2, so that's going to mean we have a factor of x minus 2, but how do we find the other ones? Well, remember how, since we know the formula for this graph, the function, if 2 is indeed a 0 or a root, so when does x minus 2 equal 0? At the 2. And then take your coefficients. We can do a little synthetic division here again from the last lesson. Hopefully you understood how to do that. Coefficients of all of your terms. If it skips any, don't forget to leave a 0. This one didn't at 3, 2, 1, 0. First term comes down, multiply, bring it up, add straight down, multiply 2 times 3, 6, put it up here, add straight down, multiply 2 times 3, 6, write it up here, add straight down. Remember, when you get a remainder of 0, that is a factor. So what's left after we factor that out? Remember, this is your number, these are your x's, these are your x squareds. So we have an x squared plus 3x plus 3 for the other 2 roots. There's a degree 2, we got to have 2 roots then. So then just quadratic formula that part to find the other 2. So we would have x equals negative b plus or minus the square root of b squared, which is 9, minus 4ac. 4 times 1 times 3 is 12. All over 208 is 1. So our other 2 roots would be negative 3 plus or minus the square root of negative 3 all over 2 for the other 2 roots. Or if you were going to write it out, you could put the, like the x minus that for the other 2. Remember, you would have one of them that's the plus and one of them that's the minus to have the other 2 zeros. In this case, they would be complex or imaginary zeros that would actually be complex since they have both a real and imaginary part. Okay, but that's what you would do to find the other ones once you've taken out the real 0 of 2. So here's the next example. So this is like a story problem. They give us a graph and they give you the formula or function for it. And it says X is the number of lamps sold in thousands and P is the profit in dollars based on the number of lamps sold. And the question at the bottom of here says, what do the zeros of the function tell you about the number of lamps that Acme innovations should produce? So the zeros, they're saying, you've got 1 0 there and 1 0 there and 1 0 there. Well, first of all, you can't sell a negative number of lamps, can you? So right here, X, the profit is 0. And then over here, the 0 there, the profit is 0 again. So P was profit here, was it not? Their profit P. Okay, so then where is our max profit? It looks like it's probably someplace right in between these 2 zeros. Okay, now the next thing would be though, how do we find all those zeros, and then from it, how do we estimate where this point would be? So the first thing I would probably do with this, first of all, would be, if you look at the graph, let's go back and clean that stuff off from there so you can see those points. Looks to be 1, 2, 3, and then 4, 5, 6, 7, 8, 9, maybe a 10. So let's check and see if those factors do come out of that quadratic. So take out my 3 coefficients. X cubed is a -1, then an 11, -4, -60. Bring down the -1, 3 times -1, -3 add straight down, 8. 3 times 8 is 24, add straight down, 3 times 20 is 60. Good, so that one was indeed an exact 0. The 3, check. Let's try the 10 over here. So now we're going to take the 10 out of this one and see if that still works and see what's left. Bring down to -1. 10 times -1 is -10. Add straight down. 10 times -2. 10 times -2 is -20. Add straight down. So that also. So we have x minus 10. First one was x minus 3. And then this last, what's left here is -x minus 2. But if you add your 2 over, and you have -x, so that's like a -2, and that would match then also for the problem on the other side. So if we have x plus 2 here and then flip the whole thing upside down so the end behaviors are correct, because for x cubed, and x cubed should be going down on the left and up on the right. This is the reverse of that, so that would match as well for this negative out front. So with that, that would be a factored form for this graph. And let's see what else they were looking for, if they found some other stuff in there as well. It looks to me like we have the exact same thing that they did, and we said that it should be between the 3,000, isn't that what we said? Between 3,000 and 10,000. If I really wanted to know an answer for this one, I would probably, just out of curiosity, again, take that original equation of -x cubed plus 11x squared minus 4x minus 60 and jump over to like a Desmos or something. So let's see if I have a Desmos open here. Put that equation in, -x shift caret 6 to the third arrow to the right, get out of the exponent plus 11x shift 6 squared, get out of the exponent, minus 4x minus 60, I believe, was our equation. And if we wanted to know exactly that max point, if I click there and hover, so it's a little more than 7, and it would be the 108, just out of curiosity. So anyway, let's go back and finish up that lesson. And we had all of that. So how would I find the solution to this problem? I've got a cubic equal to another cubic, and I want to find where they're equal to each other. So I would think I would probably do something like, let's move everything to one side. I like to keep the leading term positive. So I'm going to subtract these over to that side, which would leave me with an x cubed over there. Subtract the 5x, so I'd have a 3x squared. Add the 3x. Add this 3x over to that side and bring down my plus 1. And so now I'm looking for where that actually equals 0. So you can always use, again, Desmos, graph it, look for your x-intercepts, your roots or zeros. But this 1, 3, 3, 1, that sounds kind of familiar. Like when we did Pascal's triangle, and you could work it out in another method, but we had 1, 1, 1, and we had 1, 2, 1, and then here we have 1, 3 from these two, 3, 1. So what do we have here? Is that a x plus 1 quantity to the, that'd be like the fourth row, right? Or is, this is 0, 1, 2, so it'd be like to the third, x cubed. So that would be one way to do that. Also, we could have taken, let's see, that'd be a negative 1 is the 0. If I take that negative 1 out of this original problem here, 1, 3, 3, 1, does that work? So bring down your 1, negative 1, add 2, multiply negative 2, add 1, multiply negative 1, 0. So that would work too, and then this could be x squared plus 2x plus 1, which does factor, I believe, into x plus 1 and x plus 1. So what's my solution? Negative 1. If you plug that into the original problem, I do believe you will see that that checks. How about an inequality? So if we graphed this polynomial, and where is it less than 0 would mean where is the graph below the x-axis? So let's see. X cubed, when does x cubed minus 16x, let's see where it equals 0 to find our zeros to start with. If I factor an x out of there because they both have an x in it, x squared minus 16, now that's the difference of two squares. So that'd be x minus 4 and x plus 4. So our zeros would be at 0 from this one. X minus 4 equals 0. Here, let me not skip any steps there. So when does x equal 0? When does x minus 4 equal 0? And when does x plus 4 equal 0? That's solved already. Add 4 to the other side. Subtract 4 to the other side. So my 3 zeros, negative 4, 0, positive 4, and then do a little analysis to figure out where is it in between those. One way to do it would be an x cubed, and it's not been flipped because it's a regular x cubed, right? So that would be coming from below, has to go through. No, none of these zeros were squared, so we saw how if it has a squared on it, it bounces off, and then it would come back down and going back up again. So again, where is this graph? What are they asking for? Less than 0. So where is it below 0? This whole arm over there and this piece in between here. So interval notation for this. So forever to the left up until I hit this negative 4. Was there an equal to on the inequality? No, so when it's 0 itself, it's not included. Then either a comma to separate it. In this program, some use a U in between, and then it would be over here from 0 to 4, where it was negative, or the graph was less than 0. The y's were less than 0 for an answer. So that's how that one would look for my answers for the solutions there. And with that, I believe that will finish up lesson 3-5.